A very good evening, everyone. Can you see my screen? Can you please confirm over chat? Yeah. Okay. So, good evening, everyone. Today, we will be uh, learning some of the fundamental concepts of computer science. Right. So, this is the last lecture of this second week, and today we have been joined by students of cohort Aravali, as well as students who have subscribed to our pro plan, and a few students are auditing our program for free. Right. Before, okay. So this completes the discussion of the assignment. So we'll move forward and see today's concepts. So today we will be studying some fundamental concepts of computer science, which is time and space complexity, right? So from a data science perspective, this is important, but not that important, right? So there are many other important concepts which are to be known, but this is sometimes you will be tested on these concepts in the coding round of your interviews, if at all a coding round is happening, right? So in case of companies like Amazon or Microsoft, you will definitely have a coding round, right? So in those cases, so it depends on company to company. So some companies take a coding round, so in which you will be given a problem statement for which you have to devise a solution, but the interviewer will push you to write codes which are more efficient in terms of performance, right? So so that is today's topic, as in how do we compare the performance of different algorithms or solutions, right? So till now you might be thinking, if I write a one liner code, that is more efficient and that looks good, right? So but that is not the case, right? So we need to be evaluating some of the inherent properties of a particular solution to classify whether it is a good code, or whether it is whether its performance is good or not, right? So yeah. So these are the two concepts that we will be studying today: time complexity and space complexity, right? So the time complexity is nothing but uh, it quantifies the amount of time taken by an algorithm to run as a function of the length of the input, right? So this should not be confused with the actual time taken to run the code, right? So that may differ from system to system, okay? Because your hardware, your operating system, your processors might be different. So this is not talking about that. So how is the time related to the length of the input that I am supposed to process, right? So that is what time complexity is. And space complexity similarly is quantifies the amount of space or memory taken by an algorithm to run as a function of the length of the input. So this length of the input is quite important, right? So it's not uh, talking in relative terms, it's talking in terms of the length of the input, right? Okay, so let's try to understand time complexity by taking a small example. Okay, so the problem is to find a integer in a given sorted list. Okay, so of course you will be able to find it only when it's present in the list, right? What would be the simple solution to this? A simple solution. So now don't think in terms of the functions and methods that are built in for lists, right? Think in terms of fundamental concepts, right? So if you had to, let's say, uh, there are 100 students in a class, and let's say only one of them has the name, let's say, Raj, right? So how will you and you don't know the name, right? So how many queries that you have to make to find out who is Raj. So let's say there are 100, students. So how many queries do you need to make? Can you guess the numbers? So in case you get lucky and encounter the like the you ask the first person in the class and he says that his name is Raj, you don't have to move forward, right? But in case let's say there are 100 students, okay, uh, and you want to know the name of who is Raj. So in the worst case, how many uh, queries you need to make in the worst case, right? So in the worst case, you have to ask 100 people, or some people are writing 99, which is exactly correct. But yeah, so because 99 will be the case when you know that Raz is present in the class, definitely. That's how when you go till 99, you are very sure that the 100th person is Raj. But in case you don't know whether Raj is present in the class or not, in that case you will have the worst case as 100, right? So you have to ask all the 100 students. Okay. So basically, yeah. So similar thing is going on in Python as well, right? So when you uh, start finding a number in a list, right? So you have to iterate through each one of these elements one by one, and so by now you might be uh, guessing that okay, so this means that if the list size is n, that is if there are n elements, my worst case scenario will have n searches or n operations, right? So this is how it is linked to the length of the input that is given. So the input that is given is this list, right? So this is the list you want to search in. So your time or your number of operations that you need to do to achieve this task of finding the integer that you in the list, that is dependent on the size of the list, right? This is what we saw in the definition as well, right? It's a function of the length of the input. So in this case, the complexity is more complexity will be in terms of the length of this list, right? So how do we write that in Python? In so you can definitely go ahead and write list to search dot index, and then you can pass the integer that you want to match, and it will return you 5, which is this index. So this is 0 1 2 3 4 and 5, right? So this is the index that it returned. Okay, but what is this method doing internally? Okay, so we want to write that here. You saw how we can write our own methods, right? But this is a inbuilt method that is already provided for lists. But what is the inherent working of that method? So it's basically querying from for I in range length of list to search, right? If the integer to match is equal to the number that I am fetching from this I, right, at this index I, if it's matching, I will say that match found at index this. Okay, so in the first iteration it will this I value will be 0, and integer to match is 13, and your list to search 0 will be 1, right? So this is the first element, so it will not match there, so it will not go inside this if block. Similarly for 3 it will not go. When it encounters 13 it will go, right, and it will say that match is found, right? But so we say that the time complexity for the above algorithm is order of n. Okay, so before going into the mathematical definition of big O, or what this O of n means, right? Just try to understand this, that since I am traversing the list linearly, the order of magnitude that uh, of time that I will encounter will be in terms of n will be linear, right? So that's why I am saying order of n. Okay, so in the worst case I will hit this limit, which is n, right? Okay. So let's now move to other types of solutions to solve the same problem, right? So how do you find a particular integer in a sorted list? So remember, this list is sorted, right? So can we, come up with a more better approach, knowing that the list is sorted, right? So what can be some of the other solutions? So this is one type of solution that I'm going to explain next. Okay, so I have stored all the elements in blocks, and these are the indexes that I have written, 0 till 15, right? Now I will go to the middle element. Okay, so I'll go to the middle element and check whether this number is greater than or less than the number that I want to find. Okay, so here we have 16, right? And our integer that we want to find is 13. Okay, so because this is a sorted list, you will never encounter this number 13 in the right side of this list, right? So it will definitely be on the left side because it will be less than 16, right? 13 is less than 16, and that's why you need to search in this part of the list and not in this part. So you have straight away reduced your problem size to half in the first step itself by just making one operation, that is comparing, your given integer to the middle point of the list, middle element of the list, right? Now, what should be the next step? Can you write over chat? What should be the next step? What should I do next to find the number 13? I have not yet found the number 13, right? So now Raj says that I have to go to the mid of left. Okay. So why would I like to do that? Because I have learned that, you know, searching for the mid value and comparing with the number that I want to match reduces my problem size by half, or reduces the time taken to solve the problem by half, because I am not searching this part of the list. So again, my problem, becomes fairly simple, wherein I have this small list and now I have to find 13. Okay. So I will use the same approach, right? So I will again go to the middle of this list, which is this element. Okay. Right. So uh, yeah, I can take the floor as well, or maybe the ceiling. So I'm just taking the floor, right? So taking this element and comparing with this one. Okay. uh, I'm comparing 8, this number which is in the middle, with the number 13. So I see that, 13 is on the is greater than 8. So I will not search in this part of the list. I will search in this part of the list. Okay. So that's why I'm going to, uh, the second part, which is, starting from 12, 13, 15, and 16. So I have reduced my problem to another half, right? And this way I can continue, right? So I again went to this part and saw that, okay, these are the two numbers that are remaining, and then again I went till 13 and I found the 13th number. Okay, so how many iterations did I have to do to reach to one number, right? So 16 divided by 2 is 8, 8 divided by 2 is 4, 4 divided by 2 is 2, and then 2 divided by 1 is 1. So from 16 to 1, I have to, break my list 4 times, right? So where is this 4 number coming from? It's nothing but 2 to the power 4, which is 16, right? Each time I am dividing by 2. So 2 to the power 4, and 4 is the number of operations that I am doing, right? Because I'm, comparing the number 4 times only, right? So here I compared with 16, here I compared with 8 or 12, whatever you can take. Here I compared with 13 or 15, right? And here I compared with, 12 or 13, any one is fine. So 4 comparisons is what I required. Uh, you know, okay. So 4 comparisons is what I required to reach find this 13, right? Of course, for demonstration purposes, I took the worst case, right? uh, I took the worst case because if I had searched for 16, I would have got in the first attempt itself, right? So I took the worst case just to demonstrate, because when we talk about time complexity, we do not leave it to luck, right? So we want to classify the algorithm as it is better than the other one in terms of in absolute terms, right? So we will always take worst case scenario when describing the performance of an algorithm. Of course, you can take the average case scenario or the best case scenario, but generally we take the worst case scenario to define the performance of an algorithm, which makes sense because we are not leaving anything to luck, right? That's the worst that can happen. So if it is performing in the worst, if it is performing better, so if algorithm A is performing better than B even in the worst case scenario, that means that will always perform better than B, right? So that's why we take the worst case scenario every time. Okay, so coming back to the point, so 2 to the power k is the number of operations that I did to reach the total number in the list, right? So there were 16 elements, I did 4 operations, so 16 is equal to 2 to the power 4. So now if I were to rearrange this, what is the number of operations that I did? It's log 2n, right? So this is the number of operations that I did in the worst case. And that's why the complexity of this algorithm will be denoted as order of log n. Okay. So just remember these concepts, that this is, taking a rough value of how many number of operations that I needed to do to achieve this. In your interviews, no one will ask you the mathematical definition of order of n. It's very important to understand the how we are reporting this complexity, right? So just try to understand this concept. I hope this log n concept is clear, because people generally don't have any problems in understanding n is square, but log n is where they say that how can the order be log n, right? So yeah, so this is how we can say that the search. So this is a very standard problem in computer science, right? So we are searching in a sorted list, and it's since we are dividing by 2 every time, we call this as a binary search, right? So we can go ahead and write our own function in Python to achieve the part that we did here, right? So we can write it, but one thing that you should uh, which must be clear by now, is I'm repeating the same set of steps again and again. Okay, so I divided by 2. I have divided the initial list by 2, and then I looked at the middle element and compared. Again, in the the smaller list, I again divided it by 2 and compared the middle element. I'm going till I find the uh, desired number in the middle element itself, right? So this is the logic that I did, right? So finally I found 13 in the middle element itself, because of course if you have gone till the point where the middle element itself has is equal to the number that you are searching, don't need to go to the left of it or to the right of it. You have found it, the number in the middle, right? So this is the logic here. We want to put this in Python, but what's the best way to write something which is of a repeated nature, right? So what are the constructs that you have learned, that helps you write that helps you write without repeating a chunk of code. So here I will be writing a chunk of code which will say that okay, I want to repeat till I get the middle element as the desired element, but till then I want to compare the element with the middle one and move left or move right. So this is definitely the thing that I'm doing, but this I am doing repeatedly. So what is the construct that would be best suited for this type of purpose? Loop is one, okay. uh, anything else? Yeah. So Chinmay says a function, right? So function helps us, write codes which are very short and crisp. Basically, you can call the function again and again to do the same task. Okay. In this case, we will be, taking a very special case, very interesting case wherein we will call the same function within itself. And this concept is called as recursion, right? So where we call the same function within itself. Okay. So of course, it will be very hard for you if you are, learning to code for the first time, because this might seem intimidating, that how could I write binary search all by myself, right? So let's not go into the writing of this function, but let's try to see uh, how is this working. Okay, is it working according to the logic that we have written? Okay. Of course, with time and with practice, you will be able to write such codes, but these are not that necessary in terms of data science interviews, right? So in data science interviews, even if it is a coding interview, you will probably not be asked to write recursive functions, right? But yeah, of course, you can practice on your own and develop a habit of writing these type of functions. But let's try to see what this function is doing here. Okay, so list to search is my original list. Integer to match is 13. Result is what result is fetched from this binary search function that I am calling, which takes 4 inputs. I pass an array. Uh, I pass a lower, limit and a higher limit. Okay, so I'm passing two numbers as low and high. Okay, these will probably be the indexes of the array that I want to pass, right? So yeah, and x is the number that I want to match with. Okay, so these are the 4 arguments that my function is taking. Okay, so here for binary search, I am providing it the list to search. The low number I am providing as 0, and the high number I am providing as length of list minus 1, which is 15. So I am basically passing these two numbers, 0 and 15, and the whole list, and the number 13 that I want to search for. Okay, so I have passed integer to match. Okay, so yeah, so this goes here. Now let's see what is it doing here. So I have received all the 4 inputs. Now I have written if high is greater than low. What is written in the else part? In the else part, it's written that -1 and element is not present in the array. Okay, so there is some case which I am checking beforehand, which directly says whether my element is present in the array or not. Okay, so let's try to see whether it will go in the if or in the else part for our given input. So for our given input, what is the value of high? High is 15 and low is 0. So 15 is greater than equal to 0. So it will not go in the else loop. It will go in this loop itself. Okay. Now 15 plus 0 is 15. I have taken the floor division. So this number mid will be 7. Right. So let's try to print the mid, whether I am actually getting 7 or not. Okay, so 7 is the first number that is printed. Okay, so it's working, and we are able to know the first set of print correctly, right? So okay, now it says that if the middle value is corresponding to the value that I'm searching for, x, right? The number in the middle, so array, and then I have mentioned this bracket, and then I'm taking this index mid. So array 7, what is there in array 7 or in the list 7? It's 16, right? So it's matching with 16, and this x has been passed as 13. So 16 is equal to 13. That is not true. So we have not found the number in the middle as of now. Okay, so 13 has not been found in the middle of the list. So if it would have found it, it would have returned the mid, right? But since this condition is not satisfied, it will not return the mid as of now. Okay. Now, move on. Let's move on to the elif part. What this says is that if this number array mid, which is 16 in our case as of now, is greater than x, it will return something. Else, it will return something. So, what is this doing? Basically, it's the same logic that I said. If I find in the middle, I will return it. If I don't find in the middle, and the middle element is greater than the element that I'm searching for, that means the number is in the left of the list, right? So if so, basically what is happening is 16 is greater than 13, so I want to search this list, right? If array mid is greater than x, that means I will search in this array, right? Otherwise I will search in this array. This is the elif part and this is the else part that you saw here. Okay, so basically my elif condition is met because 16 is greater than 13, so I will search in the first half. Okay, so how do you write the first half? So basically you are passing the same array, right? But you are asking it to consider only from the 0th index till the mid minus 1 index. So the mid index is 7, so mid value is 7. So since you have not found in mid, no point in searching in mid again, right? So mid minus 1 is the index that you are passing, right? So you are saying the algorithm to consider 0 till 6. Okay, so here I have taken 7, but don't worry. So since I have not found in 16, right, no point in taking this again, so I will just pass on this part. Okay, so I will ask it to consider from 0 till 6. Okay, and what I am searching for, that number is the same, right? So 13 is again what I am searching for. So this function is again calling the same function again, but this time with a reduced value of with the the subset of the list. And how am I mentioning the subset? By this low and mid minus 1. Similarly, in the else part, I will mention mid plus 1 and high, right? So this is how I will proceed. Okay, so this is the inherent working of the algorithm, and you can see that it's in the first iteration it could not find in the mid, so the mid index was 7. In the second index, second time it could not find, the mid was 3, but this correspond to the index in the lower half, right? So yeah, so this is how you can understand a particular function that is written, right? If you encounter somewhere. So this is how you implement a recursion or a recursive function. So one of the very useful cases of recursion is while writing the factorial function, wherein if you formulate the definition of factorial, it's nothing but factorial of n is equal to n into factorial of n minus 1, right? So each time you are you can call the factorial function again on n minus 1 and multiply it with n to get the final factorial, right? So that is one of the use cases of recursion as well. Okay, okay, so now it says that you have found an index uh, at 5s, right? So you saw how we can code this up, which is whose time complexity is order of log n. Okay, and this is very famously known as the binary search. Okay, now what if you knew the position of the number beforehand? So how many operations would be required to find the number? Can you tell me? So you know the position where 13 is, right? How many operations will it take to find the number? One operation. Why is this? This is because you know the exact position. You will say function that fetch me this number directly. This is the number that I know. So you will just match list to search, you know the position 5. So you're just equating with integer to match to see if it is matching or not. So it says true. So it just found in the first attempt itself. That is because you knew the position. So what is the order of complexity of this algorithm? Right. So this is basically order of 1 because you are doing only one operation. So it's a constant time. It's a constant time complexity is what we say, right? So now coming to the big O definition, right? So it's nothing but Fn is equal to order of g of n if there exists a positive integer n naught and a positive integer a constant c such that Fn is less than equal to c of gn. So basically it's saying that, if you have functions which are, of the nature of, let's say, n square plus n plus some constant c, right? The order of this function, if let's say, in a particular algorithm, you are, the number of operations that you are doing is n square plus n plus 1, right? So that will also be called order of n square. We will not call it as order of n square plus n plus 1. Why is that? Because n square is, n square is, when we talk about large numbers, n square will beat n in a very huge manner, right? So consider the number 2. So when 2 is compared with 4, you don't see the difference. But consider the number 100. So when n is 100, what will be n square? It will be 10 to the power 4, right? So you can see the difference, right? So when we talk about time complexities, we only will be bothered about cases wherein the input is large. In case my list is of, let's say, only 5 elements, I don't need to bother about the complexity of the algorithm itself. It's only 5 integers, and if whether it takes n square time or n cube time, it's all, very less, right? We will only be bothered about the time complexity of an algorithm only if the number n is very huge, right? So in that case, if you have, let's say, n square plus n plus 1 operations, you will call it as it is order of n square. The time complexity is order of n square because n square will beat these two terms, n and 1, right? So this is what is captured in this mathematical definition of order, right? So you need to keep just this thing in mind. So if you are able to calculate the number of operations, okay, exactly, you can, write it in a short form. So you will only see time complexities of order of 1, which is constant time complexity. Like, let's say if you are even doing, constant only 5 operations is what you are doing, let's say, okay. So let's say here in this case what you are doing is you are doing 2 operations, okay. One is the print operation and one is the operation of matching these two numbers, right? Inherently you are doing only 2 operations. So in this case also the order of the time complexity is order of 1 because, it does not matter if it is a constant time thing, right? Or whether you are doing 10 operations or 20 operations, it's not dependent on n as long as it is not dependent on n, right? So your list may be very large. Let's say it has 10 to the power 6 elements, but you exactly know the position of the element and you want to print whether it is you are matching and you want to print this boolean, right? So you have to do these two things. You know that the position of the element is, let's say, 10 to the power 3. So you will just write list to search 10 to the power 3 is equal to integer to match. So even though the elements in the list is 10 to the power 6, you are still doing 2 operations only, right? So it will be called constant time and you will denote it by order of 1, right? So big O of 1, okay? So don't bother about the mathematical definition if you are not able to get it. Just know that, um, if you have 2n operations, it will be written as order of n. If you have n square plus 2n plus 2 operations, it will be written as n square only. If you have n cube plus 3n square plus 2n plus 1, it will be written as order of n cube, right? So we will only take the number that is defining the time taken by the algorithm in a huge manner, right? So I am getting one question: are we supposed to reduce time complexity of machine learning algorithms as a data scientist or ML engineer? So you will see that you don't have to uh, necessarily go into the algorithms and see. You have to know the working of the algorithm, but you don't have to go inside the algorithm and change the working of it or make it more efficient. So these are not the type of things that you will be supposed to do. Uh, in fact, in this class we are going very deep into the fundamentals of Python, but that is not at all required in our day to day activities that we do as data scientists, right? That is not at all required. Of course, you know if, let's say, what will be the use of this, of learning this algorithm is, let's say you are working on a data set which is very huge, right? And you have two algorithms to apply, right? Both of them, let's say one algorithm is giving you an accuracy of 85%, another one is giving you an accuracy of 85%. But when you put these models into production, that is, these are being used by the end users in production, let's say in Uber, the example that I gave you, right? So in price prediction or something like that, right? If these two models, if one of these algorithms is being used, right, and now you are seeing that whenever the user requests for a price, it's taking more time if pass it through an algorithm B, which is at higher accuracy of 86%, but it's returning the output quite quickly if you are using the machine learning algorithm A, which is at 85% accuracy, right? So now you have a trade-off, that one of the algorithms is better in terms of accuracy, but one is taking more time. Okay, so in that case, if you know the working of the algorithm inherently, right, you will know what order it is, right? So if it is order of n square, or is it order of n, so you can beforehand, before putting the model into production, you will be able to judge and see and decide between two algorithms which one you should use. If the requirement is not of accuracy, and you are supposed to optimize on your time that is taken to run the algorithm, you should probably go with the algorithm A, because although it has a poor accuracy, but it's very uh, fast, right? So yeah, so this is how you can evaluate two algorithms which are both valid for your data set, but one is taking more time than the other, so you can probably go with the first one. You will not have to change the code of a machine learning algorithm and make it more efficient, because you have all those libraries, and that is a topic of research in itself, optimizing a machine learning algorithm. Okay, so yeah, if you are writing Python packages of your own, reading new algorithms, uh, and so let's say someone devised a new algorithm and published a paper, you want to make it into a convert it into a Python library. In that case, you have to know a lot of coding to take the mathematical concepts and code it up from scratch, and there you will think of more efficient ways of coding your solutions. So it's not required for data scientists, for entry level or for advanced level, because that is a totally different line of work in itself, which is mainly done by people who are very proficient in coding, right? And probably come from computer science backgrounds or from other backgrounds, but they have have a lot of experience in coding from scratch. Okay, so for data scientists, that is not a requirement. So now we will just plot uh, these curves, right? So how does the order of one look? So it is basically if I have number of elements in your input as the x-axis, and the number of operations that you need to do in your algorithm as the y-axis, then order of one would mean just a constant time. So it does not depend on the number of operations will not depend on the number of elements. So as the number of elements increases, you see that the order of one complexity algorithm will have uh, a line with a horizontal slope. Okay. Then second comes the order of log n. So as you saw here, order of log n is better than order of n, because you can take a simple example as well. So what will be here you had you did 16 operations, right? You did 16 operations to traverse the entire list. Here you did just 4 operations in this algorithm. So of course log n is more efficient than uh, n, right? So O of n is more, will take more time, and it's like number of operations will be more as compared to order of log n. So yeah, so basically it will be more flat as compared to O of n. So O of n is quite linear. You can see, as the number of elements increases, your number of operations increase. Then comes, there is a different realm of algorithms which come under uh, the category of n log n. Okay, so they have some complexities such as n log n, right? And then you have order of n square as well, 2 to the power n as well, which is a worst case, right? So and you have factorials as well. So you can just this just suits up, right? So you cannot process very large data sets with these kind of algorithms, which are order of n square or order of 2 to the power n, right? So these have very steep curves, and these are as you can see, these are horrible, right? These are excellent algorithms. This comes under fair, okay, order of n. N log n is bad, but these are horrible, right? So you will not be able to process much data with these kind of algorithms, right? So you need to be very efficient in using these algorithms, right? So you have to take special provisions. Let's say if you have uh, there is one machine learning algorithm which is db scan, right? So which is of the complexity order of n square. So there you have to take special provisions as to whether you definitely need that algorithm for your use case or not. You have to make those kind of decisions, because you will see that while implementing it is taking a lot of time if you are giving it a huge data set, right? So yeah, so these are the decisions that you need to make. So from today's class, what you should take away is you should be able to say whether an algorithm is order of n or order of log n, or order of n log n, and so on, right? So I'll show you more examples. Right, so the first thing that you should the key takeaway points are, if you are traversing the whole list, that is simply order of n, because you are doing n operations, as simple as that. In case you are dividing the problem by half and then you are proceeding with it, it is log of n. Just remember this, okay? You are decreasing the complexity by half in each step. That means it's a log n complexity algorithm, okay? And I will show you cases of n square as well. So let's go to a similar concept, which is space complexity. So as time will be dependent on the number of operations that you are doing. So that is why we quoted this in terms of operations. Space is what we say when we use the memory of the computer, right? So what is the memory that is consumed while implementing this algorithm, okay? So so this is a very big misconception that you should take care of. So space complexity uh, is a is defined as the sum of two things, right? It includes the total space that is taken by the algorithm to run, okay? So you can say that it can be divided into two parts. One is the space that is consumed by the input itself, right? And other one is the auxiliary space that you have that definitely need, because uh, otherwise your algorithm will not work. So this is the additional space requirements that you create on your own to solve the problem. But the input space is what is something which you cannot do much about, right? So input is provided and it will take some space. You cannot do anything about it. You can just try to optimize the space that is required by you to get to the answer, right? So that is what you have control of. Okay. So when we talk about space complexity, it's taking both the things, the input space as well as the auxiliary space. So it is better to talk in terms of auxiliary space only, because that is what you can control, right? So it's better to judge an algorithm based on the auxiliary space that it is consuming. Okay. So now let's take a simple example. So where I have a list which I want to calculate the sum of. Okay. So if I were to use simple for loop and not the sum function as is, right? So what I will do, I will initialize the value of sum as 0, and then I'll iterate over each and every element of this list. So from uh, range length of list to sum. So I will go till 0 and so on till 6, right? And it will fetch the element corresponding to this index, and it will sum with the variable that I have taken. Okay. So this is how finally if I print sum, it will give me the actual sum of all the elements in the list. Okay. Uh, so yeah, can you tell me what is the the space complexity of this algorithm? Any guesses? Space, I talked about space complexity. So Rohan is saying order of n. That is correct, because you have to still store the input, right? Which is of if the length of the input is uh, if the list has n elements, you still need 8 bits or 8 bytes of whatever 8 units of space. Okay. So yeah, this is order of n in terms of space. So okay, in terms of auxiliary space, this is the only variable that I am defining, right? So there is only one variable I am defining. Even if the list has 10 to the power 6 elements, I will still define only one variable, right? So that's why my auxiliary space complexity is just order of 1, because I'm not taking any additional my space the space that I take to solve this problem is not increasing with the size of the input that is provided to me, and that's why it's order of 1 in terms of auxiliary space. And in terms of space complexity, as I said, 1 plus n, right? 1 plus n is n plus 1, right? So which is you can write it as order of n. Okay, that is the space that it is taking. Okay. Okay. Yeah. So let's say I have I have another approach to do the same thing. Let's say I want to find the sum, but what I am doing right now is uh, I have taken an empty list, and there I am just appending the sum again and again, right? So what I'm doing is I am storing the cumulative sum till the time the for loop has run, right? So for I equal to 0, okay, for the first element, I'm just appending the first element to the list, right? Uh, it would be more clear if I print the sum list. So in the first iteration, I'm just storing the first element in the list. So I equal to 0, I will just store 1. In the second iteration, so when I is equal to 1, I will store list of sum 1 along with I'll sum the last element of from this list, right? Take the last element out from this list and sum it with the current number from this list, and I will append that. Okay. So I took 1 from the last list. This returned me 1, and the number that I'm getting in the first index is 2, right? 2. So 1 plus 2 is 3. Again, I'm storing 3. In the second, in the third iteration, 1 and 3 is there. So I will just pick 3 from this list, take 3 from this list and sum it up. So it becomes 6. That I am appending and so on, right? And in the end, I'm just returning the last value, which I'm saying is the total sum, right? So this is the sum list after the entire loop has run. And then I'm just taking the last element as and saying it as the sum. So can you guess what is the space, auxiliary space complexity of this algorithm? Yeah. So both are order of n because, you know, I have taken a list which has, you know, n elements. So with if the number of if the input size increases to, let's say, 10 to the power 6, I will need, you know, 10 to the power 6 units of space in this list, right, to store it. Okay, and that's why my both my complexities are order of n. Okay, auxiliary space as well as space complexity. So why is space complexity order of n? Because it's n of this auxiliary space plus the n of input. So it's 2n operations that I'll be doing, more or less, but 2n can be written as just order of n because it's still linear, right? Okay. Okay, so now I have, you know, a few more examples, and then we will move to the quiz, right? So let's say you are given two lists A and B. A and B both contain 10 positive integers. You have to find the rectangle with the maximum area that can be found using two integers, one as length and one as breadth, each one coming from one of these two lists. Okay, so basically you are given two lists A and B, right? So you need to uh, basically take the product of all possible combinations of A and B, okay, of the elements of A and B, and then you have to find the that product which is the maximum. So that will be the maximum area of rectangle that you can achieve. So basically your length or breadth has to come from one from A, and the other one has to come from B, right? So how will we write this? So you will basically, you know, have a list of areas, right? Here you will just here you will start storing the areas of the corresponding pairs, right? So I have started my iterations for A in A. So this will gradually take the values 1, 11, 4, and 9 and so on, right? Similarly, inside this for loop, I am writing a for loop again, which will iterate over all elements of B. So this is a nested for loop, remember, right? So this loop uh, will be triggered for each value of A. Okay, so let's say the value of A is 1. Let's just start printing this. Print A. So yeah, you can see for this value of 1, it will iterate over all values of B. So 1 is what it has printed. Now it will go in this loop and it will print all the values of B. So it will print 51, 29, 82 and so on. 51, 29, 82 and so on for 1. Then again it will go to 11, and then it will start printing all the elements again, right? So this is how a nested for loop works. For each of the elements of A, you will, you know, process all the elements of B. For 1 you will process all the elements of B. For 11 you will process all the elements of B, and so on, right? So this is a nested for loop. Okay, now what you are doing after each iteration is, in the areas list you are just appending A into B. So when the value of A is 1 and your value of B is 1, it will append 51 as the first number. Okay, and then it will append 1 into 29, which is 29. Third, it will append 1 into 82, right? And so on. When it completes appending all the products from corresponding to this value 1 and all the values of B, it will move to the next element of A, which is 11, and then it will start appending the products 11 into 51, 11 into 29, 11 into 82, and so on. Okay. Now, once you have populated the areas list, so it has, all sort of combinations. So can you just write how, if I have, 10 elements here in this list and 10 elements in B, how many number of elements will I have in the areas list? Yeah. So I will have, 100 elements in the areas list, because obviously, 10 into 10, because for each of the 10 elements, I will have all the possible products, right? Now, I want to take the maximum area out of this area. So this is very simple. I will store the max area variable, and I will initialize it to 0. And then I will iterate over every value of areas. So area in areas, if area is greater than maximum area, I will reassign the value of maximum area. So what is this doing? So basically, I am iterating over each of these loops. Now, if the area, so first in the first loop, it will compare 0 with the max area. So max area is this, and it will compare with the first element of the area, right? So let's try to see this separately, what this is doing. Yeah, so your area value in the first iteration is 51, because your list here areas looks something like this. So the first element is 51, right? In the areas, first element is 51, 29, 82, and so on. Obviously, this is the same as these values, because these have been multiplied by 1, right? So yeah. Now moving on. So 51 is the first value of area, and it is comparing with the value of max area, which is 0 here at this point in the first iteration. So if 0, so if 51 is greater than 0, then I'm saying that the max area is the area. So I'm just assigning the value of max area as 51 in this iteration. So why I am doing this is because I need to search for the maximum value. So I will traverse the list from the left, and I will store the maximum value till the point that I have traversed in the list, right? So the first element is what I observed as being the maximum in the first iteration itself, right? So it's greater than 0, so it's definitely the maximum, right? So I stored that as the maximum value, that saying that okay, till now whatever I have observed, till now max area is the maximum value that I have observed. Now it goes to the second element and compares the max area that you have stored with the second element. If it is greater, if the second element is greater than the max area variable that you have stored, it sees that okay, now I have encountered a max area which is greater than the previously stored area. That means I have encountered another maximum. So I need to update my previous value. So this is where the update is happening, right? So I'm just updating the max area value. Okay. Every time I'm encountering a value which is greater than my previously stored value. Okay. Okay. So finding max is very clear, right? So this is how the max function will is working in the background, right? So okay. Now I know. So this max area will be 7546, which is probably some greater number which is coming by the area, right? So this is the max area that I'm getting. You can obviously confirm this whether we have written the correct code or not. we can definitely confirm this, right? So I'll just write max of areas using the inbuilt function. So yeah, we have written the correct function. Now, can you tell me, what is the time and space complexity of this algorithm? Time is order of n square, which is correct, right? So time complexity is order of n square because if there are n elements in A and n elements in B, you have to have 10 n cross n uh, n cross n basically the number of operations that you will have to do, the append operations and the multiplier operations will be n cross n, right? Because you are doing for all possible pairs. Okay, so yeah, so basically you are doing one append operation and one product operation, but you are doing for each of the pairs. So pairs is n cross n, so it's n square. So you are probably doing 2n square operations, which results to 2n square complexity for time. For auxiliary space, can you tell me what is the complexity for auxiliary space? As in, what is the complexity that I am incurring for storing the value of areas? So yeah, areas. So space is obviously I am storing all possible combinations, which is again for this particular thing. You can see we can print the length of the areas. So length of areas is 100, which is n cross n. So I have used 100 units of space to store all the areas. So my auxiliary space complexity is also n square, right? What about the total space complexity? So total space used by me is n square, and total space used by inputs is 2n. So 2 n square plus 2n, right? Which is again order of n square, right? So space complexity is n square. Uh, Time complexity is n square, and everything is n square. Okay. So can we have a better approach to solve this problem? So this is n square, as we saw, is not a very elegant way to handle problems. Do we have any other way to solve this particular problem, which will reduce my time and space complexity? Can you write such approach in the comments? Sort and multiply max value. Binary sort of both and multiply. Huh. So Devashish is correct. So max from both and multiply. So Yagnik is also correct, right? So it's very simple. If if you can use your brain, right, and not always use Python to do all the hard work, right? So you can just say that, okay, I want to find the maximum area in this case, because A and B are separate lists, right? So I can just take one from A, which is maximum, and one from B, which is also the maximum of B, and then I'll just multiply of both of them. Why do I need to store the product of each of the areas, right? I'll just multiply both of them. Correct. Yeah. So this is how you can optimize this code, right? So in terms of space complexity, you can optimize this. In terms of time also, probably it will get optimized. So we will see. Okay. Um, can you give me a naive approach, as in here I am calculating the max of area, right? So this is uh, separately, this is a algorithm in itself, right? So calculating the max in a given list. Okay. So here I have just used order of one complexity. So I don't care about how big is the list areas. I still have a um, constant constant space, auxiliary space complexity for finding the max. Can you tell me what can be other methods which are not this efficient? What could we have done so that, let's say my uh, space complexity increases to order of n in finding the max? So probably if start storing something in a list, right? And then you start storing for each and every value. Okay. So for every element, you store the maximum you have found till now for that iteration. It will obviously become order of n, right? So, but that is not a very elegant way to do. You just want to store the max. You don't want to store each and every state of the calculation, right? So that's why every time I'm updating the max area variable. What I could have done is that, I could have kept the max area, accumulating in a particular list, right? But I have very cleverly just, I keep on updating the max area, because, the max will always be the max of, the current max and the max that I will encounter later, right? So no need to store the state of the function, right? Or the values, state of the values, right? So yeah, the approach to, as you said, we will just do two separate loops, and we will store the max in each one of them, right? So this is again order of n in terms of time, and this is again order of n in terms of time. So it's like n plus n, right? 2n times 2n operations is what I'm doing. So it's order of n in terms of time. So we have reduced from n square, where we were, doing a nested for loop, to a very simplistic approach wherein I'm just taking the max of both and then just multiplying it. Okay. So this has reduced my time complexity to order of n. Okay. What is the space complexity in this case? Can you tell me? Yep. So it's order of one. Okay. Big O of one. Okay. So I guess the concepts are clear. If you have any questions, you can put them here on chat before going to the next section, which is quiz. So space complexity, is it sum of input plus aux or just aux space? So whenever someone, asks you to, asks you about the space complexity, just clarify that there is two types of, the space complexity has two components. One is the auxiliary space, and one is the input space that it is taking, right? So maybe the interviewer also does not know this nuance. So just make it clear that auxiliary space is what I will be talking about, because that is what I can control. And then you can say that, okay, so this will also create a good impression, that saying that you know the nuances of this, right?